Okay, so let's take a look at our access point, and it's page one of the access point. We have our uh, field values here on our y-axis. We have our time here on our x-axis. We have balloon A graph line and we have balloon B graph line. What I'd like to try to do is show you an example that isn't included in the questions in this lab, but we'll use this time data and field value data to generate a rate of change so that you can see how to use the template, how to fill it out, and how to solve it with proper units. So that essentially you will have questions 4, 5, 7, and 8 with a very nice example to use with their data. Okay, so we've got in my example, we are going to talk about what is the rate of change for balloon B from time 8 to time 15 minutes. And in this case, there are 2 times. So the first thing that you should do with any rate of change problem is copy and paste the template. The template for this formula is found as a resource when you click 2.4 in Google Classroom. This is the document that comes up. So I'm going to copy and paste my formula. I'm going to put it here. And then I would proceed to fill out this formula and eventually solve it. For this mini lesson though, I want to show it step by step. So I'm going to scroll down here and show you, here's the question again. What is the rate of change for balloon B from time 8 minutes to time 15 minutes? So the first step that we have to do, which is easy to do because it's already copied and pasted from the template, is the formula. So we have our rate of change equals change in field value divided by change in time. I know that this can be sometimes a little confusing because it's written horizontally. So if we were to turn it into its normal formula positions, it would look like this down here, okay? Now, when reading both of those, they read the same way. So this formula down here would be rate of change equals change in field value. The underline is divided by time. When you read this here, same thing. Rate of change equals change in field value divided by time. Okay. The next is the substitution step, where you have to fill in the data to begin solving for the time in the question or the range that's given. Normally, in the time position, you won't need to do a subtraction if your time started at 0. Okay. So if it was, say, the first 10 minutes of time, all you really need to know is the 10 minutes because the beginning is 0. So the total difference, the change, is 10 minutes. For us, that is not the case. For this example, we are not starting at 0. We're starting at time 8 and we're going out to time 15 minutes. So when we're going to fill in this time section of the formula, which is on the bottom, I'm going to use these parentheses here. And I like to use the larger time value first. So 15 minutes. Oop, not supposed to be capital. Minutes. You can do the abbreviation or you can write it out, whatever you're most comfortable with, as long as you have units. That's all I care about. Okay. Then I'm going to subtract from it the other time, 8 minutes. And now I can solve for the difference in time between them. So the amount of time that I care about that this balloon was rising is during this interval between 8 and 15. Now we need to figure out what field value goes with the 15 minutes. And we're going to need the graph for that. So also, respectively, if I put 15 here in my time parentheses, I need to make sure that the field value that I find from the graph goes here in these parentheses so that they match together in the formula. So go over to here and we're going to look at 15 minutes. So at 15 minutes, I come up to balloon B because that's the balloon it told me I'm working with. And I know that's not exactly touching, but I'm going to estimate for the sake of this example. I'm going to come over from my graph line and I see that 800 meters is probably the closest value we're going to use for 15 minutes on this data line. So over here, I'm going to put 800 meters. And you can write out meters if you want, or you can just put an M. M is meters, lowercase m, not an uppercase M. Then for 8 minutes, I'm going to come over here, 8 minutes up to the B data line for balloon B. And I see that it is 600 meters. So I fill out 600 meters. And now I have everything for my substitution. I have my units and I have my values. Now it's time to simplify. So we're going to simplify the top first. So that is going to be 200 meters. And the bottom, 15 minutes minus 8 minutes, we will have 7 minutes. Now it's time to solve. First, do the values. So 28.6. That's what it'll be. I rounded up to the nearest tenths place. 28.6 is what you approximately get from 200 divided by 7. And then we can't leave it like that. That is not a proper answer. It's just a number. It doesn't mean anything right now in science. We have to give it some sort of meaning, and the units give that value meaning. So if I look here, I have a meters divided by a minute unit. They will not cancel. They are not the same thing. They're totally different. So we have to keep them. And we keep them literally by writing them out in formula, a formula format. So we have meters divided by minutes. What that means is meters per minute. So that is what that unit is stating to us if we were to read it out in sentence form. 28.6 meters per minute is how fast this balloon is moving. Okay. Part of what you're going to do for balloon A and balloon B is figure out how fast they're moving in each of the time ranges they give you in the questions in the lab. For the 3 discussion questions, particularly question 1 and 2, you're going to use these speed values, these rate of change speed values with their units to compare what the speed did for balloon A and what the speed did for balloon B. So you would want to refer to whether or not maybe the speed increased, decreased, stayed the same, or did something else, and use the data from your data questions like this to provide an analysis and evidence of why you chose your answer in those discussion questions or developed your analysis for those questions. Okay. So with this, utilize it to try and solve or correct your lab.